and for inviting me to be here this evening and to give a talk, okay, to the public on the topic in which I have been involved for nearly 30 years. It's a great pleasure for me to be here because this kind of a public lecture here in the National College under the auspices of the Science Forum has been addressed by the very eminent speakers in the last 50 years, and I must congratulate the present management and the previous management for their sustained interest in organizing this lecture in a very uninterrupted way for the last 50 years, bringing all topics of scientific interest, which in order to create awareness among the public and create what we call scientific temper among the public, for which Dr. Satyanarayana stood for, okay, and he sacrificed his life. I think his contribution in creating the scientific awareness and scientific temper, I think it is very enormous. But I still remember when I was a student in the Institute of Science in the 70s, Dr. Narasimha's crusade against this what we call the blind, the so-called miracles and things like that. I still vividly remember how much he used to fight single-handedly and to create this awareness, not to accept the belief, not to accept the so-called miracles, in a simple way, and to what he call the gullible public, so that the cheating of the public could be minimized or could be eliminated. Dr. Narasimha stood for it. I'm very happy to be here this afternoon to give this talk. In addition to that, although I have been living in Bangalore for nearly more than 40 years, but first time I'm coming to the National College. Although large number of my classmates came from this college, and also I had a large number of seniors, juniors who joined the Institute of Science for their post-BSc program after BSc came from this college, and I can see many people here, Venkatesh, Gautam Rao, and many other people, and I'm very happy to be here to give a talk again on this topic of the composite materials, which is a new class of high performance materials. Before I see this, the composites in general, it has evolved very significantly in the last 30-40 years. Fortunately, I am one of the first person to start working on these composite materials. In fact, in the last 30 years, so much has happened in the area of composites. In fact, the kind of a terminology which now exists, never existed 30 years ago, and it has undergone a sea change in processing, in finding applications for these materials. It has undergone considerable, significant changes in the last 30 years. In fact, I would like to share with you in the last how this has the importance of the composite materials for the societal requirements, where the performance is a very critical factor, where the lightweight is a critical factor, efficiency is the important factor. So all these things have come from these composite materials, which is generally not available in any single class of materials. Most of you know, you've been using the materials, in one way or the other. You are sitting on a chair, which is a part of it is a steel, part of it is a non-metallic material. You hear composites in a different context. The people who are riding a two-wheeler use a helmet. It's a composite helmet. You must have heard this what you call the fishing rods, golf club, bicycles, the aeroplanes. Generally you read these things in the newspapers. These materials, these appliances are made up of composite materials. Most recently, the aircraft Dreamliner 787, this also has got a considerable amount of composites. I will give you why we are moving into this kind of a class of materials, the reason for it, and what are the attributes. I will talk to you very briefly with a minimum introduction, because I know the audience is a very heterogeneous with a different background. I want you to appreciate how the composite is different from a conventional monolithic material, which you are all familiar. In your school days, in your college days, you talk about aluminum, you talk about steel, cast iron, plastics, ceramics, but these composites is a combination of all these things. So I will begin my presentation talk with this view graph. I'll just tell you how I organize my talk. Okay, the outline of my talk is, first of all, what is a composite? You are familiar mostly with I told you, metals, alloys, plastics, ceramics, okay, polymers. These are the class of materials generally you come across. Plastic chairs, you talk about it, okay. Steel chair, you talk about it, okay. But what is this composite? Okay, so what is the definition of a composite? In fact, this term composite, which is used to synthesize a new class of material, is also occurs in nature. Sometimes our food that we prepare, if it is a composite, for example, instead of eating a simple cake, if the cake is mixed with what you call this nuts, it is a tasty. So it gives you better taste. Same fashion, when you have a composite compared to the monolithic material, it performs better. So let me begin with that one. So what is the general definition of a composite? What material you call as a composite? Then what are the types of composites? This composite has become generic in nature now. It's a class of composites. You can talk about composites on days and months. People working in applied mechanics, mechanical engineers, they talk about what you call this fiber reinforced composites, fiber reinforced plastics. The NA people, HCl people, they involve with what you call the FRP material, plastic composite material. But we as a metallurgist, we deal with the metals. Since the strength of the metal that one could achieve is limited, so we moved into a new class of material, composite, a metallic composite materials. Similarly, ceramics. People working in the heat engines, jet engines, people who are used to the ceramics, like alumina, silicon carbide, they cannot withstand that kind of high temperature and we cannot provide you the necessary creep and the resistance. So they will get composite. So it's a very broad class of composite material, which I will give you different. So what are the different types of composite materials? Then how these composites are, attributes of these composites are different and how they are superior compared to the conventional materials which you are all used to. Okay, that I will give you some kind of some information. Then how coming to the law, after that, the mathematical composites, because that is the topic of my research for the last 30 years I've been involved. In fact, I was the first one of the earliest person to get into these mathematical composites. I'm very happy that we have done a lot of work. Since the audience is heterogeneous, I will not be able to give you all the research what I have done and all these things, but occasionally I just mentioned how, in what way my work in the area of mathematical composites has evolved into practical applications of these materials in the general, in the day-to-day use, in its societal requirements. Then how you break these materials, maybe briefly I will talk about it. At any time of my presentation, if you have any doubts, please raise your hands. I will try to clarify the things, because you may not have the adequate background information or it will be a little more confusing. Please feel free to raise your hands. I am very happy to clarify your doubts and answer your questions or queries, anything you have. So with this kind of outline, I will just go to the definition of a composite material. What is composite? So, the most general definition of a composite is given here. It's a material system. You call a metal, polymer, ceramic, it's called metal. It's what you call monolithic material. Material system is a combination of materials, more than one material. That is called a material system. So in this system, you have a discrete constituent, okay? The reinforcement distributed in a continuous space, which is called the metric space, and which derives its distribution characteristics from the properties of its constituents. Since the material system has more than one component, so it derives its properties from both its constituents. Then, and the geometry, how these two constituents are geometrically arranged. What is the geometry? It could geometry in the sense, the reinforcement could be a very long fiber, it could be a particle, it could be a nano-sized space. Okay? So that geometry will give you different flavor to the properties of the system. Then the architecture, the way in which this reinforcing face is arranged in a continuous matrix, and the constituents, properties of this constituents, and the properties of the boundaries. When you have two constituents, you have a boundary between them. What is the nature of the boundary? That boundary, properties of the boundary also contribute to the overall properties of the system, material system. Okay? That is how this is the general definition of the composite. This composite existed, even centuries ago. You have a natural composite. For example, bone is a composite. Okay? Similarly, brick is a composite. Okay? Then, similarly, there are many things, there existed several composites which are naturally made. Okay? These are not the nature composites. But what I am talking about is the composites synthesized artificially, which never existed prior. So these are the class of composites I am going to talk about it. In fact, we borrow the same principles. When you synthesize a composite, when you formulate a composite, we borrow all these ideas from the nature. You will borrow also from the idea from the bone, okay, from the brick. Okay, so similarly there are many other materials. How you observe the nature. Many of the scientific principles that we derive, you produce, always come from the nature. When you observe the nature of materials, whether they are flying butterfly, people talk about this aircraft. Similarly, even the preparation of the materials. When you look about our nature materials, we borrow ideas. From there we try to synthesize based on a similar philosophy, similar background to produce this artificial composite or the man-made composite. Yeah, I did not hear.
No, it's very loud.
Oh, I have to reduce it.
Can you reduce the volume?
Yeah, reduce the volume.
You need to see it.
Yes.
I called him.
Yes. Okay. Now, these composites can be classified in a different way, okay, depending upon what is the basis for your classification. These composites can be classified depending on the nature of the matrix. It could be polymer, it could be metal, it could be ceramic. It could be on the size of the reinforcement. It could be reinforcement, I told you, is one of the constituent in the composite. So it could be a fiber, it could be a particle, it could be a nano size. The nano size evolution has taken place only recently in the last 4 or 5 years, because with the advent of the availability of the nano size materials, nano size particles, so people started working, instead of fiber or instead of particle, can we incorporate a nanoparticle? So there is some success you have been achieved, and you have also seen a greater performance level when you use the reinforcement in the nano size, which I will allude to you during the course of my lecture. Then functionality. Sometimes you use a composite for a specific purpose. Small composites, this is used for sensor applications. This is not a composite in a general term. Their attributes are the same except certain functional requirements. So you can have the classification like this, the types depending upon the basis on which you want to classify. I'll just give you the 3 types of composites which existed, which still people are familiar: aerospace engineers, metallurgists, and ceramic people. These polymer matrix composites, you have basically a polymer is a matrix, and the fiber it could be a glass fiber, it could be a carbon fiber, graphite, boron, and basically the fibers you use in these polymers have a very high specific strength and high specific stiffness, and their application is limited where the weight is an important factor, and the large volume of this kind of a polymer matrix composites find application in transport applications, including the aircraft, ships, and all. Next is, of course, the temperature capability is limited. The polymer cannot go beyond certain temperature. It's limited to about less than about 300-400 degrees centigrade. The application. When the temperature requirements are high for operational purposes, then you go for a metal matrix composite, where the matrix is a metal and the reinforcement is again could be a fiber, particle, and here you have these materials are used in a slightly elevated temperature and difficult to process. When the temperature is low, it's always easy to process. As the temperature goes up, it's difficult to process. Process means to produce a composite. It becomes more difficult, especially to produce a composite with what you call repeatable properties, and it becomes difficult. Then you have a ceramic matrix composites. Here, matrix is a ceramic, and you have again a fiber like a graphite, now silicon carbide, alumina. You use these materials for high temperature, like a jet engine applications, in the engine applications, but the problem is they have a lower ductility. That is the reason why you produce you composite and what you call blunting the cracks and all, you improve the toughness. Now, with this background of the definition of the composites and the types of composites are available to the engineer, designer, and for any application engineer, I will confine myself more on these metal matrix composites because that is the area in which I have been working. Because next 1 hour I can give the sufficient material for you for me to present what are the advantages, why these are the high performance materials, what is the specific advantages you gain using these metal matrix composites compared to the monolithic materials which were used until now. So here metal matrix composites, again the definition is you have a metallic matrix under reinforcement, that is again is a continuous short fiber or a particles of nano size, okay, and you achieve the properties which is not possible possible by the individual constituents, okay. That's how when you bring these two together, synthesize and produce it in a homogeneous way, you achieve all the attributes of both the constituents, plus in addition to that there is some premium some value addition when you do this one. This is the picture really, this how it looks like. This is what this fiber, this is unidirectional fiber, this is a random short fibers or the particles. This is short fibers, these are the particles, and the other one nanoparticle I am not showing you because you cannot see the nano size particles in a naked eye. Okay, so I am just skipping that one. Okay, and these are the, see when in the 60s and 70s, early 70s, when the composites concept was developed, people were trying to produce this what you call unidirectionally aligned fiber composites, graphite fiber, aluminum composites, magnesium composites. This utility of these materials were explored for nearly for 20-30 years, but somehow it did not really take off for several reasons. One is the fabrication difficulties, secondary forming difficulties, cost-wise, and the problem of the transfer toughness. So all these things, restricted the users of this kind of material. Moreover, fiber is very expensive to produce, and after having produced the fiber, to embed in the metallic system, which was much more difficult. Okay? And working of this one material into a desired shape is much more difficult. So, it had so limited utility. Then people thought, especially the material scientists, whatever the properties that we can achieve using this long fiber, perhaps could be achieved by this kind of a random short fibers. So in the 80s and 90s, there was a greater interest in the use of this kind of a short fiber instead of a long fiber. Short fiber also took the form of what you call the viscous. Viscous was nothing but a single crystal. So a lot of work was done in the United States and all over the world. Again, the materials did not take off. The reason was the viscous is a very submicron level. There was a health hazard associated with the usage of this kind of a viscous, and again the problem of agglomeration and the cost of this viscous again restricted the usage of this material. But the material scientists don't keep quiet. When they realize the difficulties associated with those kind of fibers, short fibers, the quest continued. Whether we can again achieve some degree of the same level of properties using reinforcement, which is neither a fiber nor a part of a short fiber. So, in the 90s, the enormous amount of work was focused on the use of particle reinforced or particulate reinforced composites. These reinforcements are just about anywhere between 20 to 100 microns, which you can see, just like a powder. This reinforcement is a regular powder that we normally use. And this reinforcement is the form of a, what are the forms now? I will come to this one perhaps a little later. Yeah. So when you use maybe I will explain here this stuff before I move on to this one. I mentioned to you, in the fiber reinforced composites, you have the fibers of a long dimension, and if you look at this kind of a volume fraction of the fiber required to achieve a certain degree of improvement in the properties, this is almost 50%. Sorry, 50%. Okay? And the way in which this improvement in the properties are brought into the system, material system, to usually use of the fiber, can be explained by the use of the continuum mechanics approach. It is basically you apply a stress, that stress is transferred from the matrix to the fiber. Okay. You look at this one, I want you to remember the fibers are a very long dimension and volume fraction is 50%. In order to get any reasonable improvement in the properties to be called as a composite, you need a minimum of 50% of the fiber. When the people started working, when they gave it up, when the fibers, the cost and the manufacturing difficulties associated, people started looking at the particles are a short whisker, short fiber or whisker as an alternative reinforcement. Okay, so then these particles I mentioned to you, it's about anywhere between 50 to 100 micron size. It's just a powder. And if you look at the volume fraction, look, it's about 10 to 30%. It means for the long dimensions, for the higher volume fraction, you decrease the size and decrease the volume fraction in order to achieve the same level of improvement in the properties. Okay. Then, again, you work until the 20th century, last part of the 20th century, okay, there was a greater emphasis for this metal material. There's a lot of interest all over the world, and people did produce these materials, used for several applications, which I'm going to show it to you in the things. Okay. Then, you have some difficulties, these materials. Okay, one of the major difficulties with this material, this particle reinforced, is the ductility, the toughness. Okay, because of the 10 to 30 volume fraction of this size coarse particles, it limited the ductility of the material. When you limit the ductility, the formability of the material is get restricted. You cannot make it into shapes that you want to make it. You cannot produce a thin section. Okay, there are difficulties. So then the problem of the toughness. But nevertheless, these materials were used. But the challenge was to overcome all those difficulties. Okay, I'll show you a theoretical basis in my slides in the course of the thing. Then the then if you reduce the size further, instead of a long fiber, instead of a coarse particles, if you literally use the reinforcement at a nano size, you can achieve the properties what you can achieve with a 50% fiber with less than 5%. So that is the beauty of these nano size particles, which you can incorporate into a metallic matrix. Okay, but the difficulties I'll share with you what the difficulties are. But you can now have all the difficulties that were associated with these two classes of materials. Both the fiber and this one can be overcome while using this kind of a nano size reinforcements in a very small volume fraction. But these materials are in the horizon in the last 4 or 5 years. As a result, sufficient amount of material is still not available to conduct all the understanding, all the scientific basis of the improvement in the properties. Some of the things still are going on, and some of the reason is these nano-sized particles cannot shape the mold. What else it does? When you have this nano-sized particle, it changes the microstructure, intrinsic microstructure, and significantly brings about the boundaries, interface boundaries. Perhaps all these things contribute to this enhanced strength of this material, not only strength, toughness, ductility, literally every properties you can have here in this material, in this nanostructure. So overall, in general, the advantages of the metal-metals composites over the conventional aluminum alloys or magnesium alloys. I will give you two examples. Aluminum, we can increase the strength anywhere to the 200 or 300 MPa. Stiffness, stiffness is always constant, 70. You cannot change the stiffness of aluminum by heat treatment, by alloying, by anything, other than 70 GPa values. Okay? So if you want to use a aluminum having high stiffness, well, it should not bend under a road elastic thing. You need to change the stiffness, and that can only come from the compositing. So by compositing, you can enhance the stiffness, you can enhance the strength, you can enhance the wear resistance, fatigue resistance, creep resistance, and achieve a low coefficient expansion. For example, aluminum has got a coefficient of expansion, which is used in what you call in a thermal cycling application, in a satellite, where the temperature changes from anywhere between 200 to 300 degrees centigrade to the minus 50. So cyclic changes can change the dimensions of the material. So the satellite dimensions has to be constant. You cannot allow to change that kind of a significant changes in length, in volume. So for such material, you need a low coefficient of expansion material. So the composite provides you that route where you can use in a what you call in dimension tolerance applications, especially subject to the temperature fluctuations. So you have a low coefficient expansion. For example, aluminum has got a coefficient expansion of 25 to 10⁻⁶ per degree centigrade per unit, where alumina has got about 7 or 6, silicon carbide about 6. So if you combine this one, you can achieve a much lower coefficient of expansion which satisfy the requirements of a given engineering application. So, and properties are isotropic and it can be rolled. So these are all the several advantages of the metal-metals composites. Now, just like to tell you how we can realize by compositing aluminum with this reinforcement, you can translate aluminum into a steel, you can translate aluminum into a titanium, you can translate aluminum into a cast iron in variety of applications. Okay, this one, if you look at the density of aluminum, for example, density, aluminum is 2.7. And when you composite with this one, you can get about 2.8 to 3. What is most important is elastic modulus, the stiffness, the specific elastic modulus, and the UTS, that is the ultimate tensile strength, okay, room temperature. If you look at these values here, aluminum, how much you can change? You can see from E70 to 80, you can go up to 120. And the specific elastic stiffness from 26 to about 40, and the UTS up to 700. And these are the properties which you can see only in the steel and the titanium alloys. It means the steel which has got a density of more than 6, so up to 1/3 density you can achieve the properties of the steel, and the titanium, which is very expensive material, you can achieve those properties by compositing aluminum with any of those reinforcements. Similarly, wear resistant, you can see that cast iron is the most wear resistant material used in the your brake disc, used in many of the damping applications, the cast iron. So instead of a cast iron, you can have the same level of wear resistance. Aluminum generally is a poor wear resistance. But if you composite aluminum with this reinforcement, you can achieve the properties of the cast iron at 1/3 the density. If you are using a brake disc, which is generally made of the cast iron brake disc, and which weighs about, depending upon the size of the vehicle, or a car or a train, you can reduce the density, the weight of that wheels almost by 1/3 by using aluminum, achieving the same level of wear resistance as the cast iron. So this is the objective and the effect and beauty of this compositing with the reinforcements. I'll skip this one, okay. So now, these are the, how do you make this one? You have a two constituent, you have the reinforcement like a silicon carbide, graphite, silicon carbide alumina, which is a ceramic constituent, and a metallic material like aluminum magnesium. You know, normally aluminum is melted in an alumina crucible because it doesn't wet. Similar problem will come into the picture if you try to combine these two, what you call mismatching constituents. two unlikely friends, okay, where the two different constituents with a totally different physical and chemical characteristics, you cannot bring them together. You cannot fuse them together. It's a very difficult. So that is where the technological challenges, understanding and what you call pooling the constituents for temporarily and bringing them together. This is what the technology demands. So once you know this one, to bring these two together, you can achieve this composite. You can produce the composite. So there are several methods of producing a composite. You know that material normally exists in a solid state. You can start with a powder. That's called the powder metallurgy route. There's a casting route where you know that lots of materials are made by the casting process foundry. So you melt a material and you add this reinforcement and mix it and produce a composite. That's another way. Pressure infiltration is another process similar, except application of the pressure. In situ process is another process which I will describe you later on towards the end of my lecture, where you create this reinforcement in situ, inside the melt, by some kind of a chemical reaction. Okay? So you don't bring two separate constituents together. You start with a metal, and by injecting some kind of a chemical constituents, by chemical process, you generate these dispersions of the particles or the nanosized particles or whatever you want to do. So this is called the in situ process. Okay, now these are the difficulties. I don't want to get into this picture. Okay, so this is basically a simplest process that we developed long ago. Okay, that is the process where you have a liquid metal. Here you see here, and these are these whatever you see the kind of a small granules. These are the particles. These are little bit blown up, but these are not that kind of a size. It's only about 100 micron. So you mix them and produce a composite. Okay, and we did this work long ago, very long ago. Okay, and you can mix the constituents. You know the picture I showed you, bringing two constituents. The constituents, the matrices could be aluminum, magnesium, and the reinforcements. It could be silicon carbide, boron carbide, aluminum oxide, nitrates, fly ash. Fly ash is one of the most inexpensive reinforcement available because it's a byproduct, guest byproduct available in the nature of the thermal power stations. So we thought we could make use of this one. And so we have produced composites with all those materials that I mentioned, matrices, with all these reinforcements. This is how this reinforcement looks like under the scanning electron microscope pictorially. Okay, at the 40 to 100 microns. It's how this. You can see the fly ash is available, the spherical one is a hollow one. Okay, it's how its density is very low. So apparently when you produce this composite, it will give you very low density. So it's an advantage. Okay, and these are the various properties of the reinforcement. There must be a basis for the choice of reinforcement. Reinforcement must have a very high melting point, must have high elastic stiffness, must have a reasonable strength, high wear resistance, okay, low density, low expansion coefficient. So these are the various requirements in order to choose a reinforcement and the cost line. This is what the material that we produced in our laboratory. Okay. This is basically whatever you see the continuous matrix. This is what aluminum. These dark particles are the silicon carbide particles. You can see it's about 20 to 30 micron size particles. So when we have these particles embedded in a continuous matrix, this becomes a composite. This is a composite. This is produced the simplest in our laboratory by what we call the casting process. In fact, I wanted to tell you, just because when we did this work about 30 years back, there was no patents. People were not aware of the patents. Okay, nobody knew about patents. Even there was no interest in patents and things like that. What's this research passionate, produce something new material and all these things. So we did not patent at the time. We did not know, how to proceed about the patent about 20 years back. Okay? This is another kind of composite. This is a boron carbide composite. It's again made used in the nuclear applications. Okay? These are the extruded magnesium composites, okay, with the silicon carbide particles. And this is how the interface. I mentioned to the interface boundary between the particle and the matrix. This is the particle, this is aluminum matrix. You need to be very clean interface. There should not be any reaction product. If there is any reaction, it will deteriorate the properties. So we need to have the conditions chosen for processing to maintain a very clean interface. This is a higher level, high resolution electron microscopy. This is how it looks like. You can see the particle. This is aluminum. This is really a semi-covalent interface. Okay, and this is how at atomic level the interface looks like. So this is just wanted to bring to your notice. 30 years back, when we did the work, nobody knew, patent and all these things. Subsequently, about 10 years later, the American company, just wanted to tell you, produced this, in a more sophisticated way, they did the work and produced this patent on this one. And the company started producing these materials for a variety of applications. Okay, and just wanted to show it to you that although it's not appropriate, perhaps you can see the first paper that I produced, the first reference for that patent presentation. Okay, this is what the thing. Yeah. Now after this, realizing this one, we have now taken a patent as a nano composite. Again, it's in our name, in United States patent, we were able to do that one, first US patent on the nano composite, in our name we have taken. At that time we did not do it, but American company took a patent where, the very first reference used to our work. This is again some theoretical understanding of how a particle present in the liquid, when you mix it, gets into the solid process. So we have postulated the various models. Okay, those models are reasonably well, and I don't want to get into the models. Okay, this is what I just wanted to show you. Okay, yeah. So now, when you have these ceramic particles, generally alloys are free from large volume fraction of a coarse particles. Okay, in the alloy, for example, you have some carbides, steel has got carbides, aluminum has got some precipitous particles. But here, what we do in doing compositing, we deliberately add 10 to 20% of the particles into the liquid metal and produce a composite. So, as a result of that one, when you have these particles, you can change a variety of things during this fabrication process, including the fluidity, shrinkage, hot air. You can change the strength, stiffness, damping, creep, styling wear, erosive wear, abrasive wear. All these properties can be changed because of these particles. That's what this composite, behaves. This is again thing. And these are when you have these particles, again, various phenomena, intrinsic changes in the properties, grain refinement, age hardening characteristics, high temperature properties, damping properties, various things will change substantially. For example, just wanted to show you this pure magnesium. You can see the very large grain size magnesium. When you add silicon carbide to this one, you can see what a fine grain size you can change. Okay. So in addition to the particle, grain size changes, and a grain size changes, properties changes. Okay. You can see how the stiffness changes. Okay. As simple like a fly ash can change the stiffness. Okay. Elastic modulus of material significantly by using a fly ash, which is almost a zero cost fly ash. It doesn't cost you, but it's available. So you bring this one to the magnesium, change the properties significantly. And magnesium, which generally suffers from a poor elastic stiffness, is only about 35 parts. 37, you can take it up to 50. It is about nearly about 25% improvement in the elastic stiffness can be achieved by with low cost fly ash like cost reinforcement like a fly ash. Similarly, age hardening is a phenomenon. People are familiar with this one. It's basically getting a high hardness. Just people know the tempering, the steel tempering, things like that. Similarly, in aluminum alloys, so that age hardening phenomena. So normally you need to heat treat for 8 to 10 hours, but in the case of the composite, you can do only for 4 hours. You can achieve the required hardness. This is again the damping behavior. You can see how the damping properties change. This is the magnesium damping as a function of temperature, and as if you add the fly ash, you can significantly change the damping properties. You can see how much, nearly about 20 to 30% improvement in the damping can be found. This is the most voluminous application of the metal metals composites in the 90s of the last decade of the last century. It was focused on automotive applications, on aircraft applications for these metal metals composites. I will show you that example. The tribology, when you have a tribology means, basically when the two surfaces, moving surfaces, rubbing against each other, there's a wear. Of course, there are different kinds of wear. I don't want to talk in detail. What is the wear, abrasive wear? People who have taught this physics and particularly on the chemistry, they know what are these kinds of wear. So basically, the process of wear will change the dimensions, and when you have the dimensional changes happens, there is a lot of what you call energy wastage happens. Okay, so all these things will lead to an enormous cost. So you need to have, in a moving applications, you need to have a good wear resistant material. So this is the kind of discs that are used in the automobile car, in a car. Okay, these were generally used made of the cast iron. Cast iron, which is weighing about nearly this weighing about something like a 21 kilogram. Okay, so instead of cast iron, if you use an aluminum composite, that's 1/3 the density. Okay, then you can reduce the weight of the automobile, so you increase its fuel efficiency, reduce its emissions, so many other benefits, environmental things, noise pollution can reduce considerably. But you have to establish the composite that you make with silicon carbide has the same level of wear resistance as that of a cast iron. So we carried out a lot of work on this one, actually using the brake conditions. This is the brake pads, in the Maruti car and all, it is the brake pads, okay? This is brake pads, when you apply a brake, this comes in contact with the disc and stops the car. And the discs that were made earlier than the cast iron, now we wanted to substitute with the aluminum disc, and that's what we did, the wear test. I want to show it to you. This is the wear rate as a function of the speed. The top one is aluminum alloy, and the bottom three are the composite and the cast iron. The next one I will show you, this is where you can see the cast iron wear rate, okay, much higher compared to the composite. So the composite that we produced with incorporating the silicon carbide in aluminum has a better wear resistance than the cast iron at 1/3 the density, which made this material acceptable to the various mid-sized cars, and use this one in the regular passenger cars, which I was show you to you through a movie, okay, which we did that one for the Volvo Corporation in National Hydro Aluminum, okay, so you can show that one, yeah, that, can I, yeah, can you show me that movie? Yeah. Come back to this one here. Sorry, I'm telling too long a time, I'll stop it at here. I thought I should show it to you. At least something is saying is believing actually what happens, the kind of material that we produce.
Today's cars are developed to meet stringent customer transportation limits. Demands concerning safety, comfort and reliability are extremely high. In recent years, the environment has emerged as a parameter of fast increasing importance. In the ongoing bid to reduce fuel consumption, the car's weight is of considerable significance. Cutting the weight of the braking system promotes both lower total weight and higher comfort, since the brakes are part of the car's unsprung weight, following every irregularity in the surface of the road. Brake discs made of ceramic reinforced aluminium will last the lifetime of the car and provide benefits such as lower weight and corrosion resistance. The Volvo Fluby factory has worked together with Norsk Hydro on a development project to produce a brake disc made of ceramic reinforced aluminium. The aim was to halve the weight of the brake disc, but without impairing performance characteristics. The intention is that the increased cost of the disc will be offset against added customer value. A brake disc made of the new material has 4 times the thermal dissipation efficiency of cast iron. The downside, however, is that the maximum temperature to which the disc can be subjected is lower. The design of the disc must therefore be adapted to suit the properties of the new material. A CAD model of the disc has been developed, making it possible to simulate temperature distribution. The disc's geometry has to be optimized with regard to stresses, temperature distribution and manufacturing requirements. Direct squeeze casting is the casting process that meets the cost goals, combining high material utilization with a virtually ready-for-use form. A new tool design was specially developed for this casting process. A casting system was developed, whereby the furnace and press are interlinked to form a single unit. In this model, bars of composite material are transformed into finished flags. The molten material is pumped into the mold and is then allowed to solidify under high pressure. This process produces a dimensionally accurate flag, which is entirely free of pores. The cycle time is about 30 seconds. The production volume determines how many models will be built, which in turn promotes a flexible investment structure. It is vital that the ceramic particles are evenly distributed throughout the disc. Microscopic inspection of the cross-section verifies correct distribution. In the microstructure, the silicon carbide particles can be seen as dark patches. The machining process that is required takes place with diamond-tipped tools developed in cooperation with Sandvik Corridor. This process takes place without the addition of any cutting tools. The finished disc meets the same stringent demands on dimensional accuracy as does a cast iron disc. A special technique for surface treatment of the disc was developed. This treatment helps the disc to quickly create the important transfer layer that is needed for the disc to function properly. The brake pads have been specially developed for optimum function together with a new composite disc. The transfer layer is created the first time the brakes are applied. The transfer layer gives a robust surface with consistent frictional properties. Comprehensive testing of cars has shown that the new disc material offers excellent comfort, aligned to lower weight. Tests were carried out both in desert conditions and on the wet salt-strewn winter roads of northern Scandinavia. The braking system meets all the tough demands that are imposed on Volvo's cars. The disc of the future is lightweight, lasts throughout the car's lifetime and keeps the wheels clean.
So, the almost zero wear rate or the maximum wear resistance is due to this formation of the tribal layer, which we have shown in our paper also. And this is one layer responsible for the zero wear rate of aluminum composite. Okay, one showing a better wear rate, better wear resistance compared to the cast iron because of the formation of this tribal layer. Anyway. Now coming to the most recent work that is also interest on the nanoparticle dispersed composites. The reason why we went ahead and thought about the nanoparticle is the basis for it. In general, if you use any aluminum, any metallic material, only a fraction of the shear modulus is the strength because of the easy movement of the dislocations, plasticity and all. Is less than 0.1%, 0.2%. That is the strength of the percent of the shear modulus of any given material. If you want to really use the 1% of the strength, the shear modulus, or the basis for such kind of alloy design is you will need to create an interparticle, the barrier for the dislocation movement, having an interparticle distance of a nanometer size, less than a few hundred nanometer size. And you can achieve this few hundred nanometer interparticle only when you have nanoparticles as a dispersed size. So based on that clue, that understanding, we went ahead adding nano-sized particles or creating nano-sized dispersions in aluminum magnesium alloys. So we have done this work by direct additions as well as by the what you call the in situ pyrolysis of polymer precursors in the liquid magnesium alloys. Okay, this is the direct additions of alumina particles. We have created certain specific features, specific methods to add these particles. I don't even get into that one. Okay, so this is how it looks like. But the other one method that I talked about, the in situ pyrolysis process. It means we basically choose some kind of a polymer precursor, add it to the liquid magnesium, pyrolyze it, and produce nano-sized ceramic particles. So it is basically you use a metal polymer, produce a ceramic. So produce a ceramic of a nano-sized dispersant. And when we did that work, you can see the kind of properties that you can enhance in the magnesium. This is how the microstructure looks like. These are the dispersed sites. Okay, yeah, this is what. See, magnesium, if you use it in the engine application, magnesium suffers from very poor creep resistance. Very poor creep resistance. So this is the true strain and the sustained term of a pure magnesium. Okay, this one. When you have 5% of these nano-sized particles, you can see the decrease in the true strain. Okay, nearly two-fold decrease even at temperatures like 5 MPa or 10 MPa or even at 400 degrees centigrade. Okay, 20 MPa. Okay, so you can see this is the pure magnesium, and even at a stress level of a 20 MPa, you can get the 2 times the creep resistance that of the pure magnesium. This is possible with just 5% of the nano-sized ceramic particles. This is another graph to show you the creep resistance, and these are the data values. Okay, these are the at the different stress levels, how much the strain the composite undergoes. Okay, compared to the pure magnesium, you can see 1.8 to 10 raised to minus 2, you have 10 raised to minus 3. Okay, at 5 MPa is almost twice the value. I'll just go through this one very quickly. Okay, the one I talked about, nanoparticle dispersed composites just on the horizon. We are just evaluating the properties. Still, they are not in use. Okay, we are not tested in the actual applications. But it's a predecessor. That's the conventional mathematics composites with a particle size of 30 to 40 micron. It has found a large number of applications, which includes the crystals, okay, disc, pulleys, shards, cylinder liners. And these applications include automotive applications, aerospace applications, electronic packaging. These days, the early years, these metal mattress composites are focused only on the high volume applications. These automotive applications, pistons, cylinders and all. But more recently, because of the electronic packaging, which going through a miniaturization, these composites are finding application in the packaging applications, electronic packaging, for the two reasons. One, good thermal conductivity and low coefficient of expansion, and a completely metallic one. Then packaging becomes very easy. And where are these composites going to replace? These materials, aluminum composites replace conventional aluminum alloys, so improves the performance, efficiency. Cast iron steel, decrease the weight. Titanium alloys, decrease the cost. And even fiber reinforced composites, which are very expensive from the cost as well as the manufacturing difficulties. So these simple aluminum mattress composites can substitute any of these materials in several applications depending upon the type of application. I'll show you, these are the various applications. I'll just show you the pictures of some of this one. The pistons, cylinder liners. So this is a piston. Piston, when you have a aluminum ceramic either in the form of a skirt in the top portion, ring portion, or entire material, the piston is made up of the MMCs, it has several advantages. These advantages are the following: significant improvement in wear resistance, and because of the low CTE, coefficient of expansion of these aluminum composites, it will redesign of the piston using a tighter tolerances and resulting in higher pressure and improved heat transfer properties. Improved performance due to the lower reciprocating efficiency, lesser fuel consumption. This is the advantages of aluminum composite pistons. And the brake disc I already mentioned to you is used both in the trains in Germany as well as in Europe in many of the cars. The benefits of the use of the composites in the brake disc of the trains are many, including 50% less weight, extremely low weight, energy savings, improved driver cycle economy. And this application, these automatic these composites have been used in the brake disc and the drums are used in various cars. Cylinder liners. When you have cylinder liners, the liners made up of the aluminum composites. This is what the microstructurally looks like. You can see the advantages of the cylinder liners made up of the composite. 20% reduction in the weight of the engine block, higher thermal conductivity, thinner ANC liner contributing to the increase in engine displacement, and connecting rods. This is the company which has come out very recently. Again, nano MMCs. You can see the yield strength levels when you use this composite compared to the aluminum alloys. Drive shafts. The drive shafts that are used in the various passenger vehicles, they are constrained by the speed at which the shaft becomes unstable. Now, if you use a ANC shaft, it will help you to have a longer length, and a higher specific stiffness. The drive shafts, again you can see the specific modulus, density, and the various other properties of these composites. This is the conventional composite used until recently. This is the nano MMCs, produced by the company, the DWA company. You can see you can go much higher than this one. And one of the difficulties associated with the conventional MMCs is the ductility. You can see overcoming the ductility problem when you use the nano-sized particles. You can achieve a 7%. Is adequate for a variety of applications. And the advantages of the drive shafts enables the longer drive shaft, smaller diameter shaft, and higher critical speed, reduction in the weight of the drive shaft, reduced mass required to corrective counterweights and balancing. This is the push rods, again on ANC rods. The push rods used in the translate the motion from the cam to the wall drive. When you use this one, you can see the advantages for same length. ANC push rods gives you 50% lighter than the steel push rods, and they are stronger than the steel, stiffer than the steel, and many other advantages. This is the bike, mountain bike, race bicycle made up of the aluminum composites. The parts that include both the frame, and the wheel crank and the wheel rims. This until recently they used to be made by the MMC, conventional MMC. Now with the availability of the nano MMCs, able to produce the fastest bike in the world, okay, and lightweight. In aerospace applications include the ventral fin and this engine guide vanes in the Pratt & Whitney engines, fuel access cover doors, helicopter blade sleeves, okay. This blade sleeves made up of AMCs compared to the other titanium alloys, okay, it gives you the much longer heading life. This is again an engine in the valve guide, and you must have seen in the newspapers this recent Dreamliner, you know, the usage of the composites in the Dreamliner compared to the one launched in 2007, that is 737, and one launched in 2012. You can see the 50% of this present day Dreamliner is made up of the composites, okay, and you can see, you know, aluminum is used far less, okay. Much of it is 50% composite. It makes you lightweight. You know the advantage, including the fuel efficiency of this one. This is under. Once you have the lightweight and the fuel efficiency, the comforts in the inside cabin much more better. Provide all the comforts. This is how this whole aircraft industry is moving ahead. These are the, as I mentioned to you, various benefits of the fuel exist guide vanes of the engines, Pratt & Whitney aircraft engines. Okay. This is the blades, guide vanes of the aluminum MMC for non-structural applications. Okay. I listed out various applications here. So, with all these PPTs I have showed you, and I would like to conclude my presentation, my talk. The significant progress has been made in the field of thrust metal composites since were developed in the 60s and the 70s. Now there is a greater understanding of the process, fabrication, and the formability of these materials, and the availability of the nano-sized dispersites, and understanding of the physical phenomena between the molten metal and the ceramic constituents, and the stability of this nano-sized dispersions in the molten metal. So it is now more easily possible to produce a nano-composites at a foundry level. See, these days, now you must have read in the newspaper, in the various scientific journals, the nano-sized particles is available in a very minute quantities, a few grams, a few, in a very small sizes. But it is possible to produce a large size real engineering castings having with what you call nano-sized dispersite, exhibiting all the superior properties of the nano-sized particles, okay, nano-sized composite, and variety of applications. So you can enhance its performance not only for the durability, the life cycle. You can enhance its efficiency and derive several benefits through use of these nano-composite materials. So with this one, I would like to stop my talk. If there are any questions, specific questions, I am very happy to clarify your queries.